Hello friends, now our next topic is electric field due to infinite sheet charge. Just before we have to see that infinite line charge, it is in one dimension. Now it is an infinite sheet charge, so we have to take here a infinite sheet. This is our infinite sheet filled with a positively charged carrier. Okay, now positively charged, so the according to the Gaussian surface, we have to also take here a Gaussian surface to find out the electric field due to infinite sheet charge. So we have to also take here a spherical Gaussian surface or any one of the Gaussian surface, but at the spherical Gaussian surface the distance of the each and every point are the different, so we have to choose here appreciate a cylindrical Gaussian surface. Okay, by Gaussian surface, by Gaussian law, by the Gaussian surface we can find out electric field due to the infinite sheet charge. Okay, so now take the Gaussian surface, in this case is a cylinder. Okay, now this infinite plane sheet is passing perpendicular to the axis of cylinder and the angle of dA. Okay, so here just I will make you a figure. Okay, once so what's the figure? So I will make you for here once again. Okay, this is a figure of sheet charge, and what we have to find out, just I will inform you just in one line. So this is a infinite sheet charge. Here we can fill with a positively charged. Okay, so here we can put here a positively charged. Now this is a cylinder of the Gaussian surface. Okay, this is a Gaussian surface, this is a cylindrical Gaussian surface, but this Gaussian surface we can place like that. Okay, so this is a Gaussian surface. Okay, now the Gaussian surface is perpendicular. This Gaussian surface, this is a cylindrical Gaussian surface is perpendicular to the sheet charge. Okay, now but in this Gaussian surface we have make a three-part region. Okay, this is a region, this is a region 2, this cylindrical portion is a region 1, and this end cylindrical portion is a region 3. Okay, so we have also make here now, so we can make also here there are the three region. We have to find out the three different electric region. Okay, now the region 1, for the region 1 just I will make you sure. Okay, for the region 1, this is a region 1. now we have to consider a small element of the charge. Now we have to consider a small element of the surface here. Now the electric field, now the electric field is always it is a area vector. It is a area vector. The area vector is perpendicular to the surface. Okay, and it is known as a dA. Okay, and the electric field is always passing through this surface. Okay, so now this electric field is outward, so electric field is outward and it is in that direction. It is a E vector. Okay, now the angle between dA and E is, so angle between dA area vector and the electric field, this area vector and the electric field is 90 degree. Okay, now fine. Okay, so this is our figure. Now I will show you, this is a region of 1, this is a region 1, this area vector is always perpendicular and outward, okay, of the surface, and this is a electric field is always outward to the surface. Okay, now this is region 1. Now the angle between dA of the area vector and the electric field is 90 degree, is 90 degree. So the total electric flux, now once again I will tell you what is the electric flux. The electric flux is the electric field, it is a product of electric field are passing through the surface of area is known as a electric flux. Okay, now the electric flux for the region 1 we can say it is a phi 1 is the integration of E into dA equal to close integral of, when we have to remove the dot product we can say that it is a E into dA into cos theta, but the angle between area vector and the electric field is 90. So the cos 90 value of cos 90 is 0. So the flux phi1 equal to, for the region of the flux phi1 equal to 0. Now for our second condition for the region 2. Now for region 2. Now for the region 2. Which is the region 2? The region 2 is for this disk. I will make sure, I will make you a figure for the region 2 is this. Now this is a point charge. Okay. Now this charge we can make a surface. It's a small surface area. Okay. Now we have to consider area vector is always perpendicular to the surface of this area, and it's outward is a dA, and the electric field is always outward and to the Gaussian surface. Okay, the Gaussian surface is E. So the angle between area vector and electric field is 0. Okay, now theta equal to 0 in the second case. So this is our figure. Now in figure we can say that this is a surface of the region 2, and these we have to consider a small element of the surface area. It is a area vector and this is a electric field. Okay, fine. Now for this area vector we have to find out the flux. Okay, the phi2 equal to closed integral of E into dA. Both the angle between the area vector are in the same direction, the angle will be the 0. Okay, now the angle will be the 0 and the phi2 equal to E into dA cos theta. We have to place here a 0. So our equation will be cos 0, value of cos 0 is 1. So our the value of the flux phi2 of the region 2 is E into A, and the A is a capital A is indicating the area of cylinder. Okay, fine. Now the next we have to consider as a region 3. Now for the region 3, this is our region 3. Okay, now I will make you the figure. Okay, now this is the region 3. You have to consider here a charge, and on that charge we have to create a one small surface. Okay, and the area vector is perpendicular to this point charge, this charge, and the electric field is always directed to outward of the Gaussian surface. Okay, and here also the angle between area vector and electric field is also 0. Okay, from our figure we can say that, okay, this is a region 3, and for region 3 we have to create it here a surface. Okay, for the area vector and the electric field both are in the same direction. Okay, now for the region 3, the equation of phi will be phi3 equal to closed integral of this surface of region 3 E into dA. The vector product, when we have to remove the dot product, E dA cos theta, theta is 0. So so once again we have to represent here is constant, and integration of the area is a capital A. Okay, so now the phi3 is also E into A. Now according to the Gauss law, what is this? According to the Gauss law, phi total flux equal to charge enclosed by upon epsilon 0. Now here there are the three regions, so the total flux equal to phi1 plus phi2 plus phi3, but phi1 is 0, phi2 is E into A, and phi3 is also E into A. Okay, so it's the 2 times of E into A. But here we have to consider a sheet charge of surface. So sheet charge of surface we consider as a whole surface. So we can consider as the surface charge density. Okay, now from the surface charge density is indicating as a sigma equal to Q into Q upon area. Okay, so we have to make a Q, and this is a sigma into A. Okay, so now put in the above equation. In this equation we have to put the value of Q. So Q equal to so value of the Q equal to sigma into A, so sigma into A upon epsilon 0. So sigma into A upon, so this is a 2 into EA. So this is a 2 into EA is the value of the phi. The value of phi equal to 2 into EA is in place of the Q we have to place here a sigma into A or epsilon 0. So area cancel. So electric field equation to downward sigma upon 2 epsilon 0 is a electric field due to infinite sheet charge. Okay, I hope so you enjoy this session. Thank you.